Common ion effect is a shift in equilibrium due to addition of an ion already present in the equilibrium reaction. In other words, we're just applying the Le Chatelier's principle, but we're doing math with it. A weak electrolyte is weakened by addition of a strong electrolyte that has a common ion with the weak electrolyte. Here is the equation of a weak acid dissociation. HA will break apart into H plus and A minus. If I add a salt NaA, it will dissociate into Na plus Na minus. So A minus will increase, so this will shift to the left, or the reactant side, to decrease the added stress. If I add HCl, HCl will dissociate into H plus and Cl minus. This will increase the H plus concentration, so it will shift to the left, or the reactant side, to remove the stress. So common ion effect is just Le Chatelier's principle with numbers. First example, what is the pH of a solution made by adding 0.3 moles of acetic acid? Ka of the acid is 1.8 times 10 to the negative fifth, and 0.30 moles sodium acetate to enough water to make a 1 liter solution. First thing you want to do is write an acid dissociation equation, because Ka is provided here. The acid given is acetic acid. So my equation is HC2H3O2. It's going to break into H plus C2H3O2 minus. These are all aqueous. And now I'm going to set up my ice table, because we have initial concentration and we want the equilibrium concentration, because we are looking for the pH. And to find the pH, we need to find the H plus concentration. So the acetic acid, we begin with 0.30 moles per 1 liter. Remember, it has to be in molar, so this is 0.30 molar. My initial concentration of the H plus is 0, because nothing is provided. However, my concentration of C2H3O2 minus is not 0, because sodium acetate is added. When I have sodium acetates, this would dissociate into Na plus and C2H3O2 minus. My initial concentration of acetate ion is going to be also 0.30 molar. The change will be 1 to 1 to 1, so on the reactant side it will decrease by X. On the product side it will increase by X. And to get the equilibrium, add the IC. So this is going to be 0.30 molar minus X. 0 plus X is just an X. And then 0.30 molar plus X for acetate ion. My equilibrium equation Ka is equal to products over reactants, which is equal to H plus C2H3O2 minus over HC2H3O2. So now I substitute in. X is equal to H plus. Acetate ion is 0.30 plus X divided by acetic acid, which is 0.30 minus X. We're going to assume that this follows the 5% rule. So these will approach 0, so we could cancel them out. So the equation becomes 1.8 times 10 to the negative fifth is equal to X times 0.30 molar divided by 0.30 molar. These cancel out. X becomes 1.8 times 10 to the negative 5 molar. This is equal to H plus, which is also equal to the acetate ion. We could check if this answer is valid by the 5% rule, which says the ion over the initial concentration must be 5% or less. X we found as 1.8 times 10 to the negative 5th molar divided by initial concentration of HA, which is 0.30 molar, times 100 equals 0.01%. We could eliminate plus X and minus X because the number is so small it will not affect the answer. Now to find pH, pH is equal to negative log H plus, which is negative log of 1.8 times 10 to the negative 5th molar, and this equals to 4.74. The problem has two sig figs. And for pH and pOH, sig fig starts after the decimal. Pause the video, try this problem on your own, and then check your answer. Here we need to calculate the fluoride ion concentration and pH of the solution containing 0.1 mole HCl and 0.2 moles of hydrofluoric acid. Since the Ka for hydrofluoric acid is given, that is the equation you want to start with. So you're going to take hydrofluoric acid and dissociate it into its ions. So HFAQ will dissociate into H plus F minus. So now we're going to do the ICE table. And this is a common ion effect. We know that the initial concentration of hydrofluoric acid is 0.2 moles per 1 liter. So this is going to be 0.20 molar. We have a common ion right here, 0.10 HCl, which will break into H plus and Cl minus. So my initial concentration of H plus is not 0, but 0.10 mole over 1.0 liters, which is just 0.10 molar. Fluoride concentration is 0. When you have a common ion effect, in general, you will start with 2 knowns. That means your initial will have 2 knowns versus when you did equilibrium and you started with a known on your left side and the product side were at 0. Since it is a 1-to-1-to-1, my change will be minus X from the reactant and then plus X on the products. Add the IC to get the equilibriums. So for HF is 0.20 molar minus X. For H plus is going to be 0.10 molar plus X, and for fluorine it's just X. So now we're going to write our Ka equation, which is products over reactants. My products are H plus and F minus divided by my reactant, which is HF. Now I'm going to plug my equations in. Now I'm going to plug my numbers in. So H plus is 0.10 molar plus X times X for F minus, and my HF is 0.20 molars minus X. This is equal to 6.8 times 10 to the negative 4th. Here we're going to also assume the 5% rule applies, but we're going to double check after we do our calculations. Cancel out the plus X and minus X because it approaches 0. Plugging into your calculator, X becomes 0.00136 molars, which is the concentration of H plus and F minus. So checking the 5% rule. So percent is equal to A over HA, the initial concentration, times 100, 0.00136 molars for HF minus, divided by 0.20 molar times 100. This is going to equal to 0.68%. So the 5% rule is valid. So we could cross out the x's here. The fluorine concentration is 0.00136 molar. The actual concentration for H plus is going to equal to 0.10 molar plus X, which is 0.00136 molar. This equals 0.10136 molar. pH is equal to negative log H plus, which is negative log of 0.10136 molars, equals to 0.9941. Since it had 2 sig figs, rounded to the 2 sig figs is 0.99. For pH, sig figs start after the decimal. Pause the video, solve this problem on your own, and then check your answer. Since Ka is provided, you want to write the dissociation of the acid. And this one is benzoic acid, so we start with C6H5, COOH. This is 8Q. It's going to dissociate into H plus, 8Q, plus C6H5, COOH, 8Q, minus. We're going to do an ice table because we're looking for equilibrium. So ice, we need to calculate the initial concentration of benzoic acid. The initial concentration has to be in molarity, molar, which is in moles per volume of solution. 15.00 grams of benzoic acid. Dimensional analysis to convert the grams into mole using molar mass. There is 222.12 grams per 1 mole of HA. The volume was given to you in milliliters, so we have to convert the milliliters into liters. Milliliters, milliliters. There's 1,000 milliliters in 1 liter. This is equal to 0.61415, and there is 5 sig figs because there's 5 in the mass, which is decimal significant digits, so those zeros are significant, and in the volume is decimal significant digits, so all the zeros are significant. This is the initial concentration of benzoic acid. No other information is given, so this is not a common ion effect. It's just a regular ice table. We're going to start with 0.61415 molar, and my acid and my anion are going to be 0. Since it's a 1:1:1 ratio, this is going to be a minus X on the reactant plus X on the product. So I'm going to find the equilibrium by adding the initial and the change. Minus X, X, and X. Ka equation. Ka is equal to H plus C6H5OO minus, and my reactant is C6H5COOH. Now I'm going to plug in my values, X, X at equilibrium, and then my reactant is 0.61415 minus X. This is equal to the Ka, which is 6.3 times 10 to the negative fifth. We're going to make the assumption again. This will follow the 5% rule by canceling out negative X. The calculated X value becomes 6.2202 times 10 to the negative third molar. This is going to equal to the H plus and the C6,5, the anion. We're going to double check with the 5% rule, which just says the anion over the initial concentration times 100 should be equal or less than 5%. The anion was 6.2202 times 10 to the negative 3 molar. Initial concentration of the acid was 0.61415 molar times 100. This equals to 1.0128%, which is less than 5%, so this assumption is valid. So what is their concentration at equilibrium? So the H plus and the ion is that my benzoic acid at equilibrium was 0.61415 molar minus X. So if I substitute in minus 6.2202 times 10 to the negative third molar, this equals to 0.60793 molar. Now we need to find the pH and pOH. pH is equal to negative log of H plus. This is equal to negative log of 6.2202 times 10 to the negative 3 molars. So my pH becomes 2.206196. 5 sig figs, so I need 5, but in pH the sig figs start after the decimal, so it's 1, 2, 3, 4, 5, like 1 to the right, so this becomes 2.20620. The 9 goes up, so you have to carry 1 over. The easiest way to find pOH is 14 is equal to pH plus pOH. So this is going to be 14 is equal to pH, which is 2.20620 plus pOH. So pOH equals to 11.79380. Sig figs start after the decimal for pOH and pH. Pause the video, solve this problem on your own, and then check your answer. So how many moles of ammonium chloride must be added to 2.0 liters of a 0.10 molar ammonia to form a buffer whose pH is 9.00? Kb of ammonia is given. Since the Kb is given, this is base dissociation. In general, to write a base equation, it is easier if you react the base with water. When you react the base with the water, water becomes a Bronsted-Lowry acid and the base becomes a Bronsted-Lowry base. A Bronsted-Lowry acid must give H's away, so ammonia now becomes NH4 plus. The water becomes OH minus because it gave away an H plus. And if you look at my equations, the NH3 and NH4 plus are a conjugate pair. The water and the OH minus are a conjugate pair. So a lot of times when you have a base, it is easier if you react it with water and do a Bronsted-Lowry acid base. We're going to also do an ice table. So we know how much of the ammonia. So the ammonia is going to be 0.10 molar. Water does not count because it's a liquid, and liquids are not part of the equilibrium equation. We want to know how many moles of ammonium chloride are added. So this is a common ion effect. When I add the ammonium chloride, it's going to break down into NH4 plus and Cl minus. So my initial concentration of ammonia chloride is what we need to solve for in order to find the moles of NH4Cl. And the initial concentration of OH minus is 0. Now I'm going to write my change. Again, my reactants are going to be a minus X. My products are going to be plus X's because it's a 1-to-1 ratio. And ammonia at equilibrium, ammonia is 0.10 molar minus X. My ammonium is going to be question mark is what we're going to look for, plus X. And my OH minus is X. Since pH is given, we know the concentration of OH minus at equilibrium. 14 is equal to pH plus POH. Therefore, POH is going to be 14 minus pH, which is 14 minus 9.00, which is 5.00. 14 will not count as part of a sig figs because it is a given constant. So POH is equal to negative log of OH minus ions. This is equal to 5.00. So concentration of OH minus is going to be 1.0 times 10 to the negative fifth molars. In order to solve for OH minus, you need to divide by the negative and take the anti-log of negative 5. POH has 2 sig figs, so my answer, which is OH minus, it has 2 sig figs. Every other number we do sig figs as we did before. pH and POH, the sig figs count after the decimal. Now I write a KB equation because KB is given. It's products over reactants. It's going to be NH4 plus times OH minus over NH3. Water does not count again because it's liquid. In equilibrium, we always ignore liquid and solid. Now we're going to plug in. To make the math simpler, I'm going to leave ammonium as is, times OH, which is X, divided by 0.10 molar minus X. This is equal to 1.8 times 10 to the negative fifth. We know what X is because we calculated the concentration of OH minus at equilibrium. It is 1 times 10 to the negative fifth. So now I'm going to plug that in. And here I could even simplify a little bit. If I look down here, 0.1 minus 1.0 times 10 to the negative fifth is going to be close to 0.1, so we could eliminate that. So now I'm going to solve for NH4 plus. This equals 0.18 molar. So NH4 at equilibrium equals to my initial, which we don't know, minus X, and this is going to equal to 0.18 molar. My question mark is equal to 0.18 molars minus X. This is equal to 0.18 molar minus 1.0 times 10 to the negative fifth molar. 0.18 minus 1.0 times 10 to the negative fifth is equal to approximately 0.18 molar. And they want the number of moles. Since it started with 2.0 liters, there is 1 liter to 0.18 moles. So you began with 0.36 moles of ammonium chloride. You could also use the molarity equation, moles over volume, to calculate it, or dimensional analysis. Pause the video, solve this problem on your own, and then check your answer. Since this is a weak base, because Kb is given, I'm going to react the base with water and do a Bronson lauric acid base equation. Water is liquid, so it will not be part of the equation. Water is liquid, so it will not be part of the equilibrium equation. So the water is going to behave like the acid here, so it's going to donate an H plus, so this is going to become HONH3 plus, and then we're going to be left with OH minus AQ. We're going to set up an ice table. Initial concentration of the base is 1.0 molar. Water does not count because it's liquid. This is a common ion effect because we have this right here, the hydroxyamine with the sodium. So this would dissociate into HONH3 minus and Na plus. The common ion will have a concentration of 1.0 molar and OH minus is 0. Since this is 1 to 1 to 1, so minus X on the reactants plus X on the products. So my equilibrium equation is 1.0 minus X, 1.0 plus X. I'm going to write a KB equation because KB was given. It's products over reactants. Product is HONH3 plus times OH minus divided by HONH2. Now I'm going to plug in the numbers. So this is going to equal to 1.0 plus X times X over 1.0 minus X. This is equal to 3.0 times 10 to the negative 6. So we're going to apply the 5% rule here and then check. So these x's approach 0. 1 divided by 1 is 1 times x. So x becomes 3.0 times 10 to the negative 6 molar. And this is the concentration of OH minus. So the percent ionization is going to be HB plus over B, initial concentration, the base initial concentration, times 100. So HB plus is 3.0 times 10 to the negative 6 molar divided by 1.0 molar times 100. So this becomes 3.0 times 10 to the negative 4th percent, which is very small ionization. So the 5% rule is valid in this situation. Now we need to calculate the pH. Since the OH is given, there's two ways we could do this. I'm going to solve for POH, which is negative log of OH minus. This is negative log of 3.0 times 10 to the negative 6 molar, which is equal to 5.522878. So correct sig figs must start after the decimal. There are 2 in the number, so it's going to be right here, 2 places after the decimal. So POH is 5.52. They do not want POH, they want pH. 14 equals to pH plus POH. So 14 is equal to pH plus 5.52, which is the POH. So pH is equal to 8.48.